Hi, welcome to the video for Edexcel Physics Past Paper Solution. It is IAL Physics Unit 2, January 2017. So let's start. Question number 1. Which of the following types of wave can be used in fiber optics telecommunication system? So if you see, the fiber optics is a very thin wire in which light enters from one end and keeps internally reflected and then comes out. And remember, the important word is it is a very thin wire. Okay, so the wavelength of the wire should be equal or maybe smaller than the diameter of the wire. So if you see the options, we have ultrasound, we have radio waves. These two cannot be our option. We don't use ultrasound in fiber optics, and radio waves has a larger wavelength. Radio wave has a wavelength in kilometer. The only problem is comparison between microwave and the infrared. So the wavelength of the microwave, the order of the wavelength of microwave is 10 raised to the power minus 2. That means in centimeter. Of course, the diameter cannot be in centimeter, should be smaller than, much smaller than the centimeter. And infrared has a very small wavelength compared to the microwave. That's why the option should be A. And if you see this diagram, in this diagram, radio waves 10 to the power 3, microwave 10 to the power minus 12, minus 2, and infrared 10 to the power minus 3. It is just equal to tip of the needle. That's why option is A. Question number 2. In a piano, a note is produced by striking a stretched wire with a hammer. Which of the following describe the wave produced on the wire? Most of the musical instrument that containing a wire, they produced sound waves if the wire is oscillates in a loop, and these kinds of loop are called stationary or standing waves. And of course, particle moves perpendicularly or oscillate perpendicularly, so it is a transverse wave. So the option must be transverse and stationary. It cannot be option C because stationary waves are standing. It doesn't move, so it cannot be progressive. So A and C option we cannot think of. Only confusion is B and D, but as of particle oscillating vertically, so it must be option D. Question number 3. Which of the following would improve the level of detail in ultrasound scan? Detail of ultrasound scan is all depends on energy, and energy depends on frequency. So if you see the duration of pulses or the time interval between the pulses doesn't affect the detail. The detail of ultrasound can be affected only increasing energy of the ultrasound, and that means its frequency or the wavelength. So if you see the option B is increasing the frequency of the ultrasound, definitely it is our option. If you see the option D, increasing the wavelength, of course, if you increase the wavelength, then frequency is going to decrease. So energy of the wave is going to decrease. We need high energy. So the option should be B. Question number 4. The diagram shows a ray of light in medium 1 striking a boundary with the medium 2. In medium 1, the light has a frequency f1 and the wavelength lambda 1. In medium 2, the light has a frequency f2 and the wavelength lambda 2. Okay, this is medium 1 and medium 2. This is incident light. Okay, which of the following is necessary for total internal reflection to occur? Total internal reflection. That means medium 1 is high refractive index, high n values, then this is low refractive index, low n value. I'm using n for refractive index. So medium 1 has high refractive index, must be has have a high refractive index, and medium 2 should be with the low refractive index. That's why the condition for total internal reflection. And if you see the relation, A on B cannot be our option, because in refraction frequency does not change. It doesn't matter it is coming from high to low or low to high. Frequency does not change. Only quantity changes during refraction is the wavelength. So if you are coming from low to high refractive index, the wavelength is decrease. But in this case, because of total internal reflection, that means medium 1 is a high refractive. So this is from denser to rare medium. So wavelength should be increased. That means lambda 2 must be greater than lambda 1. So C is our option. Question number 5. A source of EMF with no internal resistance is connected across a negative temperature coefficient thermistor. Negative temperature coefficient thermistor. Okay, the current in the thermistor and the potential difference across the thermistor are measured. The temperature of the thermistor is increased. Which of the following will be observed? A decrease in current. Remember, this is all about thermistor, and thermistor is negative temperature coefficient. What does it mean? If you increase the temperature, then resistance is decreased. That causes increase in the current. So A cannot be our option. NTC doesn't affect the decrease in the potential difference, because they are not talking about are there any other components, so we cannot sure about this. Okay, yes, an increase in the current is quite evident in this case. Option B and option C we can only discuss if it is said that some other component is also connected with the thermistor, then we look for option B and C. But in this case, it is not said that any other component is connected, so we see only change in the current. So increasing temperature, decreasing resistance, so increasing the current, option is C. Question number 6. Which of the following equation does not include any SI based quantities? It should be quite easy question. Yes, of course. If you see the first option, time is involved there, so it is SI based quantity. Time is also there, SI base quantity. This is also SI base, in which current, this is also SI base quantity. Only option remains as the last one, D. This is work, this is charge, and this is voltage or potential difference. So option D, equation W equal to QV does not contain any SI base quantity. So option is D. Question number 7. Diagram shows a ray of light passing from a glass to the water. And which of the following is correct expression for the refractive index for the light passing from glass to water? Okay, so the idea is if we have a medium 1, I'm calling it M1 and M2, and a light is entering from medium 1 and then medium 2, and we have a refraction. So remember, this is the normal line and this is incident angle and this is refracted angle. So angles are always measured from the normal line, and if you have a two medium of different refractive indexes, then refractive index from medium 1 to medium 2 is n is equal to sine of I divided by sine of R. This is the formula when we say that two different refractive index of medium of two different refractive indexes, and this is from n1 to 2, then sine of I over sine of R. If you see this diagram, this is your incident ray, this is your refracted ray. Please don't confuse the angle X and an angle Y. They are not incident angle or refracted angle. Angles are always measured from the normal line, so you will have to figure out, because the normal line is this. That means this is your refracted angle, which is of course angle of refraction is 90 minus X, and this angle is 90 minus Y, and it's going from glass to water, so medium 1 to medium 2, so refractive index should be sine of 90 minus Y divided by sine of 90 minus X. So the option is B. Question number 8. A water waves meet a small gaps in a barrier. Which rows of the table correctly describe the speed and the wavelength of the water waves after passing through the gap? It's all about diffraction. Okay, and in diffraction, because medium does not change, only a wave is spread out after passing through a gap, so the speed and the wavelength does not change. Only in refraction, wavelength and the speed changes, depends on the refractive index of the two medium. But in diffraction, because medium stays same, so speed and the wavelength stays same, so option is D. Question number 9. The wavelength of the progressive wave is defined as the distance between adjacent points on the wave which have the same displacement, have the same amplitude, are in phase, are in antiphase. Okay, so if you see the wavelength, they are talking about the wavelength. The general concept of the wavelength is distance between two consecutive crust or two consecutive trough. So this is the crust and this is another consecutive crust. So this distance is a wavelength, or this is the trough and this is the trough. You can say this is also a wavelength, lambda. But they are not talking about crest and trough. They are trying to check the concept, actual concept of the wavelength. So basically, the wavelength is the distance between two adjacent points which are in same phase of the motion, meaning if you see this point, Then with respect to this point, we have another point after this crust. These 2 points would be in same phase. If you measure the distance between these 2 points, this distance will also be a wavelength. So it cannot be a displacement, because displacement is all about vertical displacement. So displacement we measured vertically from the mean position. So if this is the mean position, the green line, then displacement is all about the vertical position. Amplitude is the maximum displacement. This is the amplitude, so we cannot have option A and B. Don't think about it. The only thing, antiphase, no, of course antiphase we have two particles like this, and if you take another particle here, these particles would be in antiphase, but the blue points on this wave are in same phase of motion. So distance between these 2 points would be the wavelength. So option is C. Question number 10. A potential difference is applied across a sample of a metal wire so that there is a current in the wire. The charge carrier and the wire have a drift velocity v. Without changing the applied potential difference, a second identical wire is placed in parallel with the first wire. What is the drift velocity? Okay, so if you see the drift velocity, the equation involved, the drift velocity is called transport equation, and which is I is equal to NA Q V. V is the drift velocity, Q is the amount of charge, A is the area of the conductor, N is charge density. So if you rearrange, if you make V as a subject, so V is equal to I upon NAQ, meaning drift velocity depends on mainly area and the current. So because they are talking about identical wire, so area is not changing, we need to look at what happens with the current. Now for current, you see V equal to IR. Remember, don't confuse with these V. This V is the drift velocity. It's good if I can make it curve. This is velocity and this is the voltage. So V equal to IR, that means I is equal to V by R. Wires are identical, so resistance is same, and they are not changing the potential difference applied across each wire, so V is also same. That means current remains same in both conductor. If current remains same, then drift velocity does not change. So option must be B. Question number 11. A student is investigating a relationship between current and the potential difference for a component. He does not have access to power supply, which can apply a varying potential difference or PD. He decides to use a length of resistance wire to control the potential difference applied across the component. The student could use a wire to set up a potential divider or as a variable resistors in series with the component. This is a circuit for potential divider. This is resistance wire, okay, and this is variable resistor circuit. Okay, state the advantage of using potential divider circuit. There is only the main difference between these two circuits is, if you use a potential divider circuit, you can vary the resistance present in the circuit from 0 to maximum. But in variable resistors, you cannot make a 0 resistance present in the circuit. There must be some resistance involved in variable resistance circuit. But in potential divider, in fact, you can make zero resistance and you can start from zero to some maximum value, but you cannot make it zero for resistor circuit. So that's how you can differentiate these two circuits. Question 11 part B. The student use a wire of resistance 24 ohm, calculate the diameter of the wire, resistivity of a wire 1.2 10 to the power minus 6 ohm meter, length of the wire is 50 centimeter. It is diameter. Okay, it is a quite straightforward question. You just need to use only one equation, which is you say that R is equal to rho L by A, because you need to find the diameter. So you can rearrange. First you can find A, and then you can use A is equal to pi r square to figure out the diameter. So let's just rearrange the equation and make A as a subject. So A is equal to rho L by R, and you have a resistivity which is 1.2, length 50 centimeter. Don't forget this conversion into meter. R is the resistance 24 ohm. So this is your R, this is your length after converting meter, and this is your resistivity. If you plug in all the values here and you do your working, the area would be 2.5 into 10 raised to the power minus 8 meter square. And you know that area is area of cross section, and you need to find diameter. So if you have a wire, so this is the radius and this is the diameter. So you know that area is pi r square. You can use this, you can figure out the radius, and double the radius you can find the diameter. Or you can directly write A as pi d square by 4 equal to that number, and you do your maths, you can figure out directly the diameter. And I guess the diameter will be 1.78 into 10 raised to the power minus 4 meter. This is the diameter of the wire. Part C, question number 11. Another potential divider of length 40 centimeter and the resistance 50 ohm has a potential divider of 12 volt, potential difference of 12 volts, potential difference of 12 volt applied across its length. The potential difference is measured across 7.16 centimeter of the wire. Calculate this potential difference, because these are talking about potential divider circuit. So in the potential divider circuit, what do? We, for a simple circuit, we consider we have R1, one resistance. In series we have R2, and we connect it with the power supply. So what happened? The voltage of the power supply V is distributed or is divided between the resistors. So in fact this V is V1 plus V2. According to the resistances, it is divided. That's why it is called a potential divider. And for potential divider, we have one most important relation between voltages and the resistances. So that means you can say V1 upon R1, the ratio between voltage and the resistance is as same as the voltage of the second resistance to, or you can say R1 upon R2 equal to V1 upon V2. There are different way to look at this. And moreover, you can use this directly because you have I guess you have a V1, you have R1, okay? But because they are doing, we have one more concept because they are using length of the wire. So you can imagine, because resistance is directly proportional to the length. So you can use length as a resistance. That means you can consider that you have a length of a wire that is L1, you have another wire of length L2. So if you are using two wires of the length, wire of different length as a resistance wire, so the same relation can be written in terms of length as V1 upon L1 is equal to V2 upon L2, because you need to figure out second potential difference, that means V2. So you can rearrange V2 is equal to V1 L2 divided by L1. So this is your L1 first length, L2, and this is your V1. So you can put all the three numbers and you can calculate V2 is 12 times 7.16, it is time, divided by 40. In this case, you don't need to convert this centimeter into meter. If you wish, you can convert, but it's just a waste of time. But don't need to convert. Why is that? Because we have L2 upon L1. We are dividing two lines, so unit doesn't matter. You use meter or centimeter, your answer will be same. So if you solve this, your answer will be 2.15 volt. This is your V2. Thank you very much. That's it for this video. We will see in the next or part 2 for the solution. Thank you. Have a good time.